Hello everyone! In this video we will show you some of the techniques we use to fit our NES game Micro Mages into 40 kilobytes. In this day and age we are used to storage media that can hold gigabytes of data. That means hours of video and many days or even weeks of music. 40 kilobytes on the other hand are barely enough to store 2 seconds of music in MP3 format. When the NES was conceived in the early 80s, electronic storage space was severely limited and expensive. Only 40 kilobytes of game data are visible to the console at one time. Without additional hardware on the cartridge to switch between multiple banks of memory, this is all the space developers could use, and none of the early games could go beyond that. As a result, these early games were usually very limited in scope. With one famous exception, Super Mario Bros. Its developers managed to cram in a large number of horizontally scrolling levels into the tiny space they had, which was really impressive for the time. Fascinated by this game, we just had to see if it was still possible to create a game with the same limitations nowadays, going back to the roots of the NES. And these were our plans. A vertically scrolling platformer with a cartoonish occult theme. The core mechanics are running, shooting magic spells, and, to make traversing vertical levels fun, wall jumping. We want to provide an adventure with many levels and boss battles that you can go on alone or with up to 4 people, as we felt the NES library was truly lacking a multiplayer experience like this. To program an NES game like this, you need maximum control and speed, so we need to speak the processor's language directly, writing all code in 6502 assembly. 8 kilobytes are used for graphics and another 32 kilobytes for everything else. The graphics are split into 2 tables, one for background elements, the other for independently moving foreground elements, which are called sprites. Each table holds 256 graphical 8x8 pixel tiles. A single sprite on the NES can use 3 different colors. You can combine multiple sprites to build larger objects, or meta sprites as we call them. The NES only supports 4 different sprite palettes at the same time. So we reserve 1 palette for each player and they have to be reused for enemies. One of the most characteristic limitations of the NES is that only a maximum of 8 sprites can be rendered on the same horizontal line. Excess sprites simply disappear. That's why a lot of games employ a flickering effect to allow more sprites to be seen. So we decided to reduce the size of the players to avoid reaching this limit and save space in the sprite graphics table. Taking Super Mario Bros. As an example, here's the space used by all of Mario's graphics. You can see that the choice of smaller sprites allowed us to bring diversity and fluidity into the main character's movements and ultimately left space for more content, for example, different bosses. Speaking of which, we had to come up with a couple of tricks to be able to store them at all. For example, these are all the individual frames used for the first world's boss. If we store the sprite graphics like this, our dream of making this NES game will end right here. So here's what we do instead. First, we split this big meta sprite into 3 parts that can be animated independently of each other. Let's decompose these parts into individual sprites and see if there are any graphics that are the same. We only need to keep 1 instance of a sprite tile and can then reuse it as many times as we need to. The NES is also capable of flipping sprites vertically and horizontally, which allows us to reduce the number of individual sprite tiles even more. As you can see, we optimized the top part quite a bit, from 16 individual sprite tiles down to 4. For the middle part, let's continue in the same fashion. The bottom part has 5 animation frames, But the last two are flipped versions of the first two. And again, we reduce the amount of individual tiles as much as possible. With these kinds of optimizations, we could save a lot of graphics space, which allowed us to add more content. In order to have a reasonable number of levels, finding a good way of compressing level maps is crucial. So let's go into that next. First, a background is made from many 8x8 pixel tiles. At 1 byte per tile, disregarding color information, a full screen would use 960 bytes. That's almost a full kilobyte, which is quite a lot. So, we add a layer of abstraction, which we call meta tiles. And then we use the same trick on those again, ending up with meta tiles of meta tiles. With this technique, a full screen will use only 60 bytes. This is a graphics table where we store all the background tiles used in the game. Here's how we build meta tiles. Each world has its own tileset, and tilesets do take up space on their own, so there are some tricks we employed there as well, but for the sake of simplicity, I will not go into detail about them in this video. Now, with these meta tiles, we can build tilesets of meta tiles. Finally, we can start building the background for one screen. Even if 60 bytes don't seem like much, the total map data of the game was still relatively large, so we searched for other ways to optimize it. And so we thought, what if the levels were symmetric? Okay, so let's remove half of the screen and mirror the left side. Ending up at 30 bytes per screen. Unfortunately, the gameplay suffered from this. It quickly became clear that completely symmetrical levels were too bland and just not fun to play. But wait, there is a solution. Expanding on what was mentioned earlier, one meta tile on the map is stored as an index into the tileset and uses 1 byte. 1 byte is made up of 8 bits. In our meta tilesets, we only use a limited number of tiles. So, as you can see, the highest bit will never be used in the tileset index. That means that, at 4 meta tiles per row, we can use 4 bits to store another value. We use these 4 bits to enable shifting the mirror axis of individual rows of tiles, breaking up the symmetry and allowing for more diverse level design while still only using 30 bytes per screen. Of course, let's not forget that levels are much bigger than just a single screen, so the cumulative savings achieved by all the aforementioned techniques are quite substantial. Finally, all of these saved bytes allowed us to add a hard mode. In those classic games that have one, hard mode often means something along the lines of play the same game again but with more resilient enemies. With the remaining space, we wanted to provide a more unique challenge than that. Adding new tricks to the enemy's repertoire was possible. Designing completely new levels, on the other hand, not so much. Well, let's see what we ended up with. Changing the existing level's palettes is an easy trick that does not use many bytes. To make changes in the level layout, we opt for updating tiles in key locations only. With this method, the hard mode level data ended up using roughly 7 bytes per screen on average. It's a bit of a generous statement, but you could say this allowed the game to have twice the amount of content at the total extra cost of only a couple hundred bytes. So, now you know some of the tricks we used to make this game possible. We are glad to present this project to you and hope you will enjoy playing it as much as we enjoyed making it. Thanks for watching.